Alright, this is a big one, the kinetic theory of gases. The kinetic theory relates microscopic quantities, position, velocity of a gas bopping around inside a container, to macroscopic properties like pressure and temperature. We're going to have a set of assumptions here. One of those assumptions is that there's a whole bunch, capital N, a whole bunch of identical molecules of mass m inside a container of volume V, and each will act as a point particle bouncing off of each other. The molecules move randomly and will always obey Newton's laws. The collisions with other molecules and with the walls are elastic. This is going back to momentum from back in the old days, simpler times. So remember, we could have elastic collisions or inelastic collisions. These are all going to be elastic collisions. In elastic collisions, momentum is conserved because momentum's always conserved, but kinetic energy is conserved as well. So here's the deal. Let's narrow our focus down to one dimension, just the x-axis going across this container. Our container is in 3 dimensions, but right now we're only concerned with the x-axis. We're going to take this particle of gas that can move in 3 dimensions and confine it to move in only 1. If it does, there's some basic assumptions we can make. Hey, you know what? It's going to go back and forth across the walls of the container. It's going to hit one wall and come back and hit the same wall again a little bit later on. So the length, the round trip length, is 2 times the length of the container. So remember pressure? Pressure equals force over area. Force is going to be mv squared divided by the length. And then area is the length squared. So what do we have here? mv squared divided by length cubed, mv squared divided by the volume. Alright, so in the kinetic theory it turns out that not every molecule has the same speed. Their speeds are represented by the Maxwell distribution and will depend on the temperature and mass of the molecules. So if we have a situation where nominally the temperature is 300 Kelvin, the particles that make up that gas at 300 Kelvin have a distribution of speeds. Some are relatively slow, some are exceedingly fast. We heat it up to 1100 Kelvin, then that distribution spreads out and we get another average value. Alright, so here's the deal with the kinetic theory. We just stuck with 1 dimension just then, but there's actually 3. So if we divide it up or expand it to 3 dimensions, pressure equals 1/3 capital N, the total number of particles, divided by the volume, mv squared. Now this average is going to it's not really the average, it's the root mean squared average. We'll talk about that in a minute. But for right now, here's what it boils down to. The kinetic energy of our gas particles is proportional to the temperature. So 1/2 mv squared equals 3/2 kT. Now that velocity that we might figure out for a gas particle is an average value. Remember, we have our Maxwell distribution and they're all over the place. But the average speed, the root mean squared speed, root mean squared isn't exactly the same thing as average if you're into statistics. I'm going to take all the values and square them and then get the mean value and then take the square root. So it's going to be different than the average, but it's a statistical way of talking about what the mean speed would be. So here we have a case where we're looking at this root mean squared speed is slightly greater than the most probable speed and the average speed. So the most probable speed for a particle is here, the average speed is here, and then the root mean squared speed is here in this distribution. Alright, so the kinetic energy. The internal energy, now we're really getting close to the stuff that we're going to build into thermodynamics. The internal energy of an ideal gas is the sum of the kinetic energies of all of its molecules. So in this case, where each molecule consists of a single atom, we can have the case where U, the internal energy, equals 3/2 n, the total number of particles, times kT. So we get a sense of the internal energy of a monatomic ideal gas. That gas, just because it's sitting there on a shelf at a certain temperature, has a certain amount of internal energy. And if we can harness that energy, we can do work with it. That'd be pretty cool. But on a practical level, let's look at this situation. I have a sealed container with water molecules in here. Those water molecules, some of them have really high energy, so much energy that they jump from the liquid phase to the gas phase. So if I have an open cup sitting on my table, just at room temperature, some of those water molecules will jump into the gas phase and will get carried away, and eventually my liquid will evaporate. Here in this sealed container, they'll jump into the gas phase and then they'll reach some sort of equilibrium, because in the gas phase some of them will slow down and jump back into the liquid, and some will jump into the gas phase. And so long as the temperature is maintained at the same temperature, we have this equilibrium vapor pressure. I don't know if you've heard of that before. Water boils when the vapor pressure equals the outside pressure. So when you heat up water to the point that the vapor pressure is the same as the pressure outside, then it jumps into the gas phase, and that's when water boils. Well, here at sea level, that happens at 100 degrees Celsius. But if we climb up to the top of a mountain, maybe the pressure is so much less that our water would boil at something closer to 90 degrees Celsius. That's not a great thing if you're familiar with trying to cook. When you cook something in boiling water, you cook it at 100 degrees Celsius, and then it takes some time. If you try to boil your spaghetti at 90 degrees Celsius, it would either take a lot longer or it might never cook properly. A pressure cooker is a specific device that is arranged to maintain a higher pressure than atmospheric pressure. Therefore, your water boils at a significantly higher temperature and your thing will cook faster. Alright, so phase equilibrium and evaporation, the vaporization curve determines the boiling point of a liquid. So different factors can change where the boiling point is, and we can figure that out with a vaporization curve. And that will explain why water boils at a lower temperature, at lower pressure, and why you should never insist on a 3-minute egg in Denver, Colorado. So here's pressure versus temperature and what goes on with our water, H2O. So it's solid phase ice here at certain range of pressures and temperatures. And if you get cold enough, then it almost doesn't matter what the pressure is. It's a gas here, higher temperature, low pressure. It's a liquid here at a certain range of pressures and a certain range of temperatures. It would be a liquid. And then we'll get to this point where you reach this critical point and you can have a supercritical fluid under certain temperature and pressure conditions. That's something that might be of use to you at some point in your scientific career. But that's a phase diagram that explains relative to pressure and temperature what phase, solid, liquid, or gas, or maybe supercritical fluid, your substance is in. And there's different phase diagrams for different materials. So it's not just water, there's other materials that we might be interested in. And that is enough. I kind of go through all the there's another set of images, so we don't need to look at those as well.